I'd like to welcome Jolin Morel and Georg Ripenberger from Massey University. They're looking at sheep milk freezer, which will extend the life of milk for processing to get around the distance between producers.
Alright, I'm Jolin Morel and this is Georg Ripenberger, and we're working on a rapid milk freezer. This work is part of the FIAT program, so that's Food Industry Enabling Technologies, an MBIE funded program that aims to grow New Zealand's food exports through the use of new technologies. So the aim of our project is effectively to bridge the gap between a small producer and a processor. So if you're a small producer, you might not produce the volumes where it's economical to have it regularly picked up to an outside processor, so you need to therefore make your own added value products. And on the other hand, if you're a processor, you might find it difficult to get a number of small producers. So what we need is some way of aggregating and storing several collections or milkings worth of milk before it can be sent off. So what is sometimes used is freezing the milk. However, this freezing is generally done using a slow freezing method by putting bags like these of about 10 to 15 to 20 litres in glass chillers. And this can lead to some issues such as losses in cheese yield, changes in the total solids, components of milk, separation and oxidation of fats into some rancid flavours, reduced protein digestibility, increased renneting times and decreased curd firmness for those cheesemakers. And so there have been several proposed explanations for this, and they all basically revolve around the idea of freeze concentration. So when you freeze a solution or a system of particles in it, as the ice front grows, it rejects the solutes and the particles and forms pure ice. So this leads to the unfrozen fraction of milk concentrating, which leads to physical aggregation of the milk. The milk components can lead to ice crystal damage as slow-growing ice crystals damage fat globule membranes, and changes in the salt balance and the acidity of flocculation can lead to protein flocculation and protein sedimentation. So, how do we propose that we'll be able to prevent this? Basically, we aim to do it by freezing milk quickly. So, if you look at how the solutes in a salt solution are rejected as a function of the growth rate of the ice. As you see, as you grow the ice faster, more of it is trapped within the ice. So we assume that by growing our ice very quickly, so in other words, about 60 or about 30 times higher than has been studied in these previous studies, we have trapped the components of the milk within the growing ice layers, and therefore prevent degradation. And another area where this is looked at is the material science world and something called freeze casting. And what they have found is that above a critical velocity called VC here, you can actually trap all of the particles within your moving ice front. So for one study, this moving ice front, which would trap 1 millimetre particles, 1 micrometre particles I should say, is about 30 micrometers a second. So at the start of this work I originally discussed last year at the conference, and saying that we were beginning a 3-year development plan. So the original way we aimed to do this was to freeze it as a droplet, as can be seen here. And these were frozen by immersion in liquid nitrogen. So how do we achieve this? Immersing in a cryogen is obviously very expensive, it's hazardous, so it's not really suitable for a low-cost on-farm solution. You could use a prilling tower, so you drop droplets against cold airflow, but this would be very high and would therefore be very expensive. And a new technology that's arisen in the past 10 years are what are called superhydrophobic surfaces, where water basically sits on top of the surface and doesn't wet it, so the water sitting on the surface will roll. And this would allow us to roll droplets down a series of inclined plates, so this is just to get a larger throughput per second, against the cold airflow and then freeze. So this is just effectively a description of a super hydrophobic surface. So in 2015, there was some proof of concept work done on this using a drum, a spinning drum placed in a freezer with a super hydrophobic coating on the inside, and droplets were placed in the freezer, and we imaged how long it would take to freeze these droplets. And as you can see, after about 40 seconds, we ended up with nice 3mm droplets of frozen water. So this was what we were planning to do until about July. At that point, we were starting to run into some issues with the fabrication costs of these surfaces and the system, and with the uncertain ice phobicity of these systems. So in some cases, in condensing atmospheres, we've got a lot of moisture, you can actually end up forming frost on those surfaces, which then leads to ice forming directly on the surfaces. And in an array of stacked plates like we had, this would lead to blockages in between the plates, which would lead to obviously a blockage in the system. You'd have to heat the whole thing up to try and clean it out, and it wouldn't exactly be an robust, reliable, on-time system. So we moved to a new setup, which George is going to describe.
So yeah, we had to come up with a new plan, and so the idea as well. We look out what's already available, and instead of reinventing the wheel, and there are different ice machines available, and they got all different names like flake ice, shell ice, whoever makes them, they're different. And sometimes they're used on fish trawlers, so you can keep your fish fresh. And how it essentially works, you have a drum, and you have coolant in the inside, and then you pick up your cold drum, and the ice layer forms, and you scrape it off. And then it's generally just used for fish or for frozen vegetables as well. And there's lots of different designs, like that's a design you use in fish trawlers, which is vertical. So you spray your liquid on, and then you got a screw which sort of separates the ice off. And so if we base it on that one, the advantages is that they are commercially available. It's a proven principle, and hence it's cost effective to do so. We have decided to go for a falling film freezer, which essentially works by distributing coolant in the inside of a vertical tube and the product on the outside. And then in the next step, an ice layer forms and it grows outwards. And the advantages of using a falling film is that we achieve high heat transfer coefficients, and that's back to what Jolin said. We need to have a high ice growth front in order to trap all the particles we want. And then once we have a desired ice layer thickness, we just turn off the product flow to temper the ice, because we don't want to get wet ice or wet frozen product. And then comes a product detachment phase, which there are several possibilities to do that. One is heating a thin layer and then let it drop by gravity. Alternatively, we are looking at things like GNS, with just using mechanical actions to remove the ice. And as I mentioned, the advantage is good heat transfer, and we have minimal of moving parts if we use a falling film freezer. And there's already some commercial claims that people have used it for vegetable or fruit juices, and they reckon they can retain 20% of the solid. And so there are some challenges in it. We need to investigate what is the desired ice growth rates, and what are the heat transfer coefficients and what we need to achieve, and also obviously process regulations. As soon as you start freezing something on site, you actually have a processing step, and we have contact with MPI, and that needs to be investigated further that we comply with all processing regulations. And then other things like product detachment, as I mentioned before, and food safety, of course, and does it meet our product quality requirements as well. And how does it look like? Well, that's a CAD drawing of our system, which is built at the minute as we speak, and you can see some of the work going on in the workshop. And about 3 weeks or 2 months, we hope the pilot scale unit is operational, and we're looking to install that on a sheep farm and trial it in about towards the second half of this year. And if people are interested and they would like to trial it, please get in contact with us, or if you're interested in some products or generally you'd like to try something, please contact me or Jolin. And that's just a little update from our project at Messi. Thank you.
Thanks, Jolin and George. That was interesting. I must ask, what's the reason for freezing rather than just holding it 2 degrees, for instance?
Well, freezing allows us to store it over a much greater period of time. I mean, if you look at the studies, if you get it, freeze it fast enough and store it cold enough, you can actually get good product storage for periods of up to, say, 9 months. So if you have a, 2 months is what you're, 2 years. Yeah, okay, the studies I see looked up to 9 months, maybe they got bored after that point. So yeah, it allows for a much longer storage time.
Thank you. Any more questions?
So what about transport costs? Because then if you freeze it on site, then you've got to you have to transport it frozen, and surely that's a lot more expensive than fresh.
Well, the idea, if you transport it fresh, you have to process the milk within 3 days at the absolute maximum from collection, I believe. So you'd need to be travelling far more regularly if you were transporting fresh milk than if you were transporting frozen milk. If you're only making a couple of 100 litres a day, it's not really economical to send out a tanker every day. However, if you have a weekly or 2 weekly pickup of a tonne of milk, then that becomes more cost efficient, simply because you're not doing this regular transport. So even though the requirements for frozen refrigerated truck might be slightly higher, you're doing it a lot less regularly. And
But you have to store it frozen, obviously, on site.
yes, so we're looking at ways that this can be done economically.
What's the plant cost estimates?
The current cost estimates? Well, for our pilot unit, which has got more instrumentation, so it's a bit more expensive, but our pilot scale is about 50 litres per hour, and that is around 20,000. And that's including a lot of instrumentation costs.